Hi everyone, and thank you, Raphael, for the introduction, and thank you to all the organizers for the invitation to come talk here. So, as Raphael mentioned, so I did my PhD with Denis Bernard, who introduced me to quantum trajectories, the same way he discovered a bit about it. So I was a theoretical physicist. Now I work mostly with mathematicians. It just says that as a bit of warning. So I will use terms like theorems and lemmas and things like that. Don't be frightened by it. I tried to adapt a bit to come back to my roots in physics, but I may not be very efficient at it. So please interrupt me if anything is not clear. And also, if you have some questions, of course, if I don't go through all my presentation, it's completely fine. Actually, I would prefer, so that means that you understood at least what I talked about. So I will talk about something. So my motivations then are a bit different. I don't want to necessarily compute things. I want to understand what here is the asymptotic behavior of quantum trajectories. So can I say that they have a generic behavior under some assumptions, and so that basically I don't have to compute everything each time, but I can know that if I have some properties, I know that it will behave always a bit of the same way. And I will do that under with and without purification. And we'll see purification, we didn't hear about it yet, but it's actually something very important in quantum trajectories. It's a property specific to quantum trajectories that you will see is related to what can we learn about a quantum state given indirect measurements. So this work is basically a presentation of what we did with some collaborators in the first paper in 2017, and a more recent one with a postdoc, Anna Stepanek, who is now working in Milano with Wojciech. So first, the third time of the day, you will see this picture, and I'm pretty sure you will see it even more during the conference, because it's a prototypical example of experiments of quantum trajectory, which is really easy to understand. So as Pierre mentioned, what happens in the experiments that you have what I would call a system here in a superconducting cavity, which is just monochromatic, trapped monochromatic light. And it is probed by two-level atoms, Rydberg atoms, going through the cavity, being prepared in some state and measuring another one. What is interesting here, I will go a bit quicker more abstractly in this talk, is that what you obtain at the end of the experiment is this kind of data set. It's a sequence of measurement outcomes. It's just that. And all you do, all your computation, you do it only with that. So if I go a bit more abstractly, so I have some probes, what Pierre called meters, that are independent, copies of each other, if you like, and they will interact with the same system each time, unitarily. And for now, that's all. I won't talk about measurement for now. So how can I describe it like mathematically? This system is just, the system state is just a density matrix. I will denote it that way. And the evolution is given by a quantum channel, so a trace-preserving completely positive map. Meaning that I can write the evolution that way, with a sum over conjugation by some Krauss operators, and with some index J. So this choice of matrices is not unique. And if you don't know about it, there is a neat little theorem called Stein-Spring deletion theorem that tells you that if two families of matrices describe the same quantum channel, then they are related by some unitary matrix. So, sorry. Okay, so first thing, without measurement, still, I do the average. I just don't care about what is the outcome of my measurement. And some irreducibility condition, if you know about Markov chains, irreducible Markov chain is exactly the same thing, but it's adapted to quantum channels. Then I have actually convergence, like exponentially fast convergence of the average evolution of my system to a steady state. So this is like a theorem proved by Evans and Kron in 78. So you can see what happens here on the block sphere. Like I have like many different starting points, and you see that they will all converge towards the steady state here. You don't see it here, but it's inside the ball actually. So this is the first generic, like this kind of result. This is this kind of result I am looking for. Like, do I need to care about the initial state of my system when I look at the evolution? Here, what it tells you is that in a long time, you don't care. So let us now introduce measurements. So now I put some apparatus that will measure and record, especially, the outcome of the measurement after the atoms go through the cavity. So all the statistics of this outcome, so these are random and they have some statistics, so I can actually summarize in the Krauss operators. So the kind of experiments they can model, there's already been mentioned, like all the quantum optics experiments, of course. But you can also think in terms of what is called collisional models in quantum stochastic thermodynamics. And also, like a more recent application of that, I won't talk about, is quantum circuits with measurements. So, which is kind of important because there is a strong belief and strong indication that there is some new phase transition appearing in these setups. So what is the behavior of the outcomes? I'm just looking at the outcomes, not the underlying trajectory for now. So the measurement outcome is just a sequence of measurement outcomes. So for the more probabilist and mathematician among you, it's just so omega will be my measurable space. And so I introduce some kind of dynamic on this sequence that is a dynamic that gets rid of the first measurements. This is usual definition we use to understand some behavior, like ergodic behavior of the system, of the outcomes. And we have a probability measure, which is just provided by quantum mechanics. It's just given by the Krauss operators, product of Krauss operators. And for those who know what it means, so that the dynamical system here defined by omega, theta, and p rho here is actually ergodic. It should be rho steady state here, sorry. Is ergodic. For those who don't know, and you may not care actually, what you can see is that if you have exponential clustering in time, if I take a function f and g of the outcome at time 1 and at time n, then they will behave as if they are independent, plus some corrections that decay exponentially fast. That's the idea of like this implies ergodicity, if you like, but this is like a strong behavior that yeah. But we have actually more than that. That's like here, so it looks like independent, but it's actually like more than that. That essentially all the asymptotic behavior of my outcome will behave as if there were independent copies of one outcome. So first of all, we have the law of large number. So if I look at the number of times I solved the outcome j up to time n, and I look at the frequency of it appearing, then it will converge with probability 1 to the probability to obtain the outcome j in the steady state. So this is one generic behavior. You have also some perturbation around it. If you go to the next order, so in square root of n, actually it was proved so in 2015 basically that this frequency of appearance of nj to order square root of n behaves like a Gaussian random variable. So it's really like, you will like Gaussians, of course, especially in physics, because we know that we can compute everything with Gaussians. So we have this generic behavior, so we are happy with it. And you have many other of these results that are true. Like we have a large deviation principle for those who know. We have actually a speed of convergence for this, for the approximation by Gaussian. We have like all the measurements, all the limit theorem you can think of basically are known now, except for one thing which is quite important, is that we don't know exactly how to the parameter estimation of such models. That I want to estimate a parameter. I want to estimate the parameter in my Krauss operator here using the outcomes. And that we don't know if it falls into the usual models of asymptotic normality. So does it look like a Gaussian model asymptotically? Why it's important this? Because if you know that it behaves like a Gaussian model asymptotically, you have many algorithms that are open to you that you know are optimal to estimate your parameters. So maybe I didn't say that before, but to connect with what Pierre's talk, you have remarked maybe that here I don't consider that we can have error in detection. So I have perfect measurements here. I will come back to imperfect measurements at the very end. So we have that for the outcomes, but we are in a conference about quantum trajectory, so let's turn to quantum trajectory. So what is quantum trajectory? It's basically looking at this evolution of the system, but condition on the outcomes. Condition that, okay, after time n, I saw J1 to Jn, what is the state now of the system? And quantum mechanics tells me that it will be actually defined that way. And if you define it that way, it's quite trivial, and actually Pierre mentioned it also, that this defines what a Markov chain, so a system without memory, essentially, or memory only on the present, which is defined that way. So that at time n+1, I update the state at time n using the Krauss operators Vj with probability given by Vj, Krauss operators Vj. One thing which is important, if you remember, I talked about time spring deletion before. Here you see that it depends actually. My quantum channel didn't depend on what choice of Vj I used. Here it depends drastically on it. But what is the choice of Vj or Wj as before? And it's just choosing what observable you are measuring on the probe. So changing what you measure on the probe changes what the dynamics and the quantum trajectory you have. So now, given that we know how to update our system state given the outcomes, question is, if we don't know what is the initial state of our system, what can we know about our system just using the measurement results? And to discuss about that, I need to introduce a notion which is particularly important in quantum trajectories. It's a notion of dark subspaces. So what is a dark subspace? Is a subspace of your Hilbert space, of your system Hilbert space. So it's a subspace of CD here, which has dimension at least 2, else it's kind of trivial. And on which I want that if I act with any product of my cross operator, it's as if I acted using a unitary. Maybe random, but a unitary operator. Meaning that if I restrict my system to this dark subspace, it behaves like an isolated evolution. An isolated evolution that may be mapped to other dark subspaces, but you will see later that if I map back to the same dark subspace, it's as if I evolved, I had a closed, an isolated evolution. Why is this notion important? The first reason why it's important is that in 2006, Kummerer and Maassen proved that the entropy, the von Neumann entropy of my system state actually vanishes almost surely if and only if I don't have these dark subspaces. So if I think of the entropy as the lack of information I have about what is my system state, it means that I know exactly, I have extracted all the possible information about my system state, and I know perfectly my system state, if and only if I have no dark subspaces. So then what I will say is that you may expect that since the entropy vanishes only on pure states, I will say that if you have no dark subspaces, we have purification. So if I give some examples of simple purification, Pierre told us about one this morning. If you remember, he had some convergence toward a pure state. Random one, but a pure state. So in our Roche experiments, we have purification in the dispersive case. We have purification if and only if I can identify each one of these Fock states, which are called pointers here. Or for a qubit, if I'm looking only at a qubit, that either all my cross operators are proportional to unitary evolutions, or I have a purification. Why? Because for qubits, d equal 2, so the only dark subspace you have is the full space. The full space. So what is interesting also about this, like I said, that we can think of purification as obtaining all the information possible about a system state. And this was basically the intuition that led us to a first preliminary result of an important result I will state afterwards with some collaborators. That we showed that basically you can estimate your state without knowing the initial state if and only if you have no dark subspace. So if you have purification. So just looking at the outcome, I know after a long time, I will actually know what is the actual state of my system. And I didn't write it here, but the convergence is actually exponential, exponentially fast. Yes?
In practice, can you come back to the first line? In practice, how do you know if it exists a mu or not? What is the most simple numerical check?
So this is a very good question, of course. Here, actually, so this is a definition, which is, okay, you can, I try to motivate it physically, but besides for qubits where it's obvious because you just have to check if you have unitary operators, like as soon as you are in dimension 3, it's hard. And I will show you some examples afterwards why it's actually hard to find these subspaces. And actually these subspaces are also important in quantum information because you can use them, and I will mention it after, as some kind of error correcting codes.
And the name dark subspace comes from where? So
dark, it was given by Kummerer and Maassen, is the idea that you have no light shining out, so you have no information on them. In this idea here.
Okay.
And also this idea here, that if you have a dark subspace, then you can never know what happens inside. Yes.
Right. So the dark subspaces, it seems not very mathematically speaking, but like the measurement process has not that much access to that subspace. So is there any, I mean, maybe it's a trivial reason I can't see, but is there any reason why the dimension has to be 2 or more? Like is it possible that even a single one-dimensional subspace could be not accessible?
So, like given the definition here,
yeah.
So basically, any one-dimensional subspace is a dark subspace.
Okay.
Because it's really like it's dark because you cannot know, like the measurement outcomes cannot distinguish about what happens inside. But like but inside a one-dimensional subspace, you know what it is because it's a one-dimensional subspace. Okay. Is there any other question for now? Let me continue. So just to illustrate here what this behavior that you can always construct basically this estimator, which will be like well known to some of you maybe, and maybe will come up in Pierre's lectures. That basically you start computing your quantum trajectories with the chaotic state, initial chaotic state, and then it's a good estimator. And you can see here on this picture. So in red is the estimator, in blue the truth trajectory, and you see that they exponentially become like superposed. So one consequence, important consequence about that, I told you about, like, I want to know when are the quantum trajectories like behaving generically in long time. So if you have no dark subspace and you have a unique invariant state, I forgot to mention, but I will always assume that I have this convergence toward a unique steady state. Then we have actually a unique invariant probability measure, meaning that if my state in law, so the law, the distribution of my state will converge always to the same one. And you can see it here. So I have multiple quantum trajectories that start from the same point, and you see that they will be distributed. And so there is still a bit of movement because it's in convergence in law, not almost sure, to some distribution here on this part of the block sphere. This is in convergence in law.
It's the law of Rho n which converges to.
Yes, the law of Rho n converges to, and the convergence in some metric is exponentially fast and everything. So the proof is quite simple, that we estimate the true state with the estimator, with a good estimator, and then we use the ergodic properties on the measurement outcomes. And we have the proof. And this convergence actually comes with other limiting behavior that again look like independent copies of the same law. So independent high-ID random variables, if you like. So the first one is a kind of a strong law of large number, that if you take the C0 average of your state at any time, then it will converge to the steady state. Actually, it's much more than that. You can take like way more complex function of your state, but let's keep it at that for now. And also, to the next order, you have again a central limit theorem, that it behaves if I look at, for example, the average of an observable along my quantum trajectories, and I look at how it behaves at the order square root of n, then it will look like a Gaussian. So again, it's a generic behavior that we would expect. I mean, you would like to have some maybe new behavior, but we don't have it for now. The question is that here, all this is with dark subspaces, without dark subspaces. So the question is, what happens when we have dark subspaces? So let me first give some examples of dark subspaces, so it will become clearer now what I will talk about. So first, if I take the Krauss operators to be basically unitaries, like proportional to unitaries, then actually the full space is a dark subspace. Just applying random unitaries, so I can never know what is my state. And the outcomes actually are completely IID independent of my state. What I can do also is put some unitary for each outcome. What I do, I have some Krauss operators on one qubit and the unitary that depends on this outcome on another qubit. This is described here, and then any subspace that is just, I choose a state in the first qubit, a pure state in the first qubit, and the full space of the other qubit is a dark subspace. And it's not the only one, because you could expect that, okay, maybe it's the only possibility of dark subspaces, but it's not the case. For example, in dimension 3, you can use these Krauss operators here, and you can see that this space here, like I will call E1, is mapped to itself, and it sends the second one, E2, to itself, using some unitary transformation here. And so I have some dark subspace. What is it? This example, the dimension 3 example, is exactly that. I have two planes, and my first Krauss operators either does a rotation in this plane or projects from this plane to this one, doing also a rotation. And on this second plane, I have V2 that does a rotation or sends from V1 to V2 using a rotation. So these are non-trivial dark subspaces. Now the question is, and as Raphael asked, how can we characterize these dark subspaces? And this is like actually a difficult question. So first, as I said, a dark subspace is a subspace in which, looking at the outcome of the measurement, I cannot distinguish between two states that are in this subspace. I can take two states that are supported in this subspace. Just looking at the measurement outcomes, I cannot distinguish them. So this, you could think of like it's a downside to having dark subspaces. An upside to having dark subspaces is like you can control well what happens in the dark subspace. Because if you have a dark subspace and you start with your initial state in the dark subspace, then you know that you can find a unitary operator depending on the outcome, such that you can actually go back to this initial state at the beginning. So this.
By the way, the mu. What you do with the mu of the function?
Mu is just a factor, so you don't care about it. Mu is just it's a proportionality. So, but since you are working on density matrices, it disappears. Mu will give you actually the probability of seeing the outcomes. And this you can see so that you can somehow stabilize some states in this dark subspace. So this is related actually to error correcting codes. And this was investigated in this paper. I won't pronounce it because I will like massacre some of the names here. So it's actually really important result here. So one remark here, which is important, is that the characterization of dark subspaces considers products of Krauss operators. If you only look at one Krauss operators, what we could call one-shot dark subspaces, basically you know that if you are in dimension high enough, or you have too few dark Krauss operators, then you have some one-shot dark subspaces. But now let's look at what happens to come back to this idea of saying, okay, do I have this unique asymptotic behavior of my state? So what can I say that is generic? I don't need to look at what was the initial state of my system to describe what is happening. So we can define what we call maximal dark subspaces, which are dark subspaces of maximal dimension. It's not that hard, because if you have like a dark subspace of large dimension, if you take any subspace, it's still a dark subspace. So you want to look at only the one with the largest dimension. And then you can define on this set of maximal dimension dark subspaces actually a Markov chain again. A bit similar to quantum trajectories. That you just take the dark subspace you are in at time n, and you update it with Vj to obtain En plus, and you know that you are still in the dark subspace because you just did a unitary rotation. And you take the probability with respect to the chaotic state, but on the dark subspace. It should be En here, sorry. It should be En. So only on the dark subspace. So you know that, so this is a Markov chain. And the two results we showed with Anna Stepanek and Clément Pellegrini, that first, your system state will concentrate asymptotically on one of the dark subspace. Like it will be a random one, but basically you can describe everything with maximal dark subspace. It's sufficient. You don't need to look at anywhere else. And the second one is that actually you have a unique invariant measure for this Markov chain without assumption of purification here, because we have dark subspaces. But of course, you only know that it's true for dark subspaces. You don't know what happens inside dark subspaces. So if I give you an example here, like in the 3D example with these two planes that are mapped to one another, the unique invariant measure is just an equidistribution between the two planes, essentially. It's not essentially, it's an equidistribution between the two planes. So you are randomly 1/2 in one of the two planes. So the question, as I said, is that we know what happens for dark subspaces, but we don't know yet what happens inside dark subspaces. And this is the purpose of the last part of my talk, last few minutes. So, as I said, that the maximal dark subspaces have the same dimension. So I can map all of them isometrically to some common space of dimension m. Yeah. And then on this CM, actually everything, all my evolution given by the Krauss operators, if I force myself to still be in CM, is just unitary element of some group, of some unitary group. I'm just doing some unitary actually evolution here on CM. Defined that way. But I take CM, I map it to E naught, the first dark subspace. Then I apply all my Krauss operators, and then I map back to CM, starting from the dark subspace I'm in, so EM. So this is a random process in the group generated by all these unitaries. And so this is a random evolution on an M-level system. So if I look at 2 qubits, for example, or two-dimensional subspace, so I have here the CM, the equivalent of CM, which is mapped by some isometry into 2 different subspace of the full subspace. And V1 and V2 can map between my different block balls here. But inside each block ball, the dynamic will be given by what happens on this common space. And the result, the first result we have is that if we look at this unitary process, like this product of random unitaries, you have a unique stationary measure for this process, which is just the R measure, so the uniform evolution, the uniform, measure on it. So one with full symmetry. As a corollary, on the block sphere of CM, of my copy of dark subspaces, we have the invariant measures are all the ones that are invariant, that are image of R measures, by the R measure of some state. So I have, I know that I have a unique invariant measure of my dark subspace. I know that if I look at only what happens inside the dark subspaces, but I don't look at which dark subspaces I'm in, I have also a uniform measure, like a classification of the invariant measures. And actually, we can put that together. So if I define that way, so that it's a mapping back of this measure that I choose randomly, according to the invariant measure, a dark subspace, and I take the R measure on my unitary process inside dark subspaces, and I map it back to the original system Hilbert space. Then I have an invariant measure of the quantum trajectory. And actually, these measures are the only invariant measure of the quantum trajectory, especially if the group I defined here is actually the full unitary group, special unitary actually. Then I have a unique invariant measure, which is just the full invariant measure on each sphere, and the invariant measure corresponding to what are the proportions of each dark subspace. So here are some examples. So I have two, here it's a 3D example actually. I have always one state which is in both dark subspaces, which is the one that is the intersection of the 2 planes, which is a red ball here. So for some of the parameters of theta and phi I had, you can have this measure here with 4 points, here 4 points. And here you see that you have 8 points if I choose differently the parameters. But this is not a minimal group. So actually what you have is not this group, but the group generated. And if you choose well, it will be the full circle. So you can have different behaviors depending on the parameters. And to each starting point, you have a different invariant measure. Another example here, if we look back at the example where I act on one Krauss operators on 1 qubit and a unitary on another one, then what can happen is that on the one where I purify, I choose one starting point here, and it will be mapped to a group here on the dark qubit. But the point is that it's not necessarily that the invariant measure here is not necessarily given by the unitary group generated by this uj. It can be actually smaller. For example, if you look at the group generated by this uj, you may think that the only invariant measure are the ones that are supported by these 4 points. But actually, you have another invariant measure which has smaller support, which is given by just these 2 green points here. So it's a bit subtle, this construction of this invariant measure, but basically what you obtain is a full characterization of the invariant measure for quantum trajectories with and without purification. And maybe to conclude, because I have only a few seconds left, there is a lot of still open question in this, for us in this field. First of all, I said that we have a behavior that is like IAD random variable, and so we can have all the limit theorem we know usually, but one thing is missing is the large deviation principle for quantum trajectories. And this is actually, this has revealed to be quite a challenge to prove that you have a large deviation principle, which, as you may know, is quite important because it has like interpretations in terms of thermodynamics and things like that, and it's, we are working on that with some colleagues. From a thermodynamic point of view, there is a question of the reversibility of the trajectory, and can we relate it to quantum detail balance? This is another area of research I didn't mention here, but which is quite important. One that is related to what Pierre talked about this morning is about like going to imperfect measurements, so that we replace just the Krauss operators by completely positive maps. And this, we have made some progress in this direction, but it's not complete. And then to look at like non-Markov model, so with some memory and like infinite memory maybe. I mean, what can we say in that case? And infinite dimensional models, we start to have some results, for example, in the example of Arroche experiments at resonance. If the states that are sent in the cavity are actually thermal states, actually we can prove that we have a unique invariant measure. This is a recent result with Laurent Bruno. But the full theory for infinite dimensional model is not done. So thank you very much.
Well, very question. I probably suppose you have a multi-dimensional dark space.
Yes.
Then I would imagine that depending on your initial condition, and depending on the particular realization of your Fourier sequence, you will end up in different points, different corners of this space, right?
Yes, so I didn't insist on it well enough. I must say that indeed, that it's what I mentioned here, that here, of course, it's for each starting point, you have a different invariant measure. Except if G is a full unitary space where you will have everything. But this is what you see here. If you start from this point, then you will have these 4 ones. If you start from this point, you will have 4 here. So it really depends indeed on what point you start from.
But not only on the point you start from, but also on the particular realization of your Fourier chain.
So that's, okay, so not exactly, actually, that is the point. Here, the result is really in low. So that you are not looking at the full evolution, you're just looking at what is the statistics at one time. What is the distribution at what time? So it won't depend on the specific, and that's the point, that if you, so you don't look at your system, you measure, you don't look at your system. You update it with the outcomes and everything, but you don't do computations, and you, for example, in a UR experiment, they verified that everything was described by quantum trajectory. What they did is that they did some tomography after, they compared doing tomography after some times and conditioning on the measurements. And this is what you would like to do, that you have some after some measurement, you will have a random state. And the point that this random state will be described by this measure here. So it will depend, like for each realization, of course, it will be different, but the statistics of it will be the same.
Hello, my name is Shishir, and I just have maybe a naive question. Has anyone looked at the connection between entanglement and dark subspaces? Like specifically the evolution of entanglement under Markovian dynamics?
Some people worked at different models. If you want to look at this question, you have to look at different models. For example, here you can see that you will have no entanglement because at the end you will have a pure state on one side and another one. So it will be completely disentangled.
I'm just wondering because if you can write within this dark subspace the Markovian evolution, so the sequential application of Krauss operators as a unitary, that would mean that you're preserving the dimensionality of entanglement within that subspace.
Yes, so you would have to cook up a model. I mean, I don't know about it, but it's possible to try to cook up a model so that a dark subspace is actually a subspace generated by entangled state. For example, singlet states, or singlet state and spin zero, m equals 0 state, for example.
Okay, thanks.
Hello, my name is Nicolas, and thank you for the talk. Do you think dark subspaces are related to the notion of recurrent and transient subspaces in some ways?
So what is more related to transience and recurrence is the group here. That basically you have, for one group, you have different orbits, and each minimal orbit will be, the one recurrent class. So we are in finite dimension, so you should think of it as the equivalent of a finite dimensional, finite state Markov chain. So you could have a transient subspace, but it won't be seen by the invariant measure, because you will exit it. So it's not related directly to recurrence and transience. It's more like a classification of recurrence classes.
But is it exactly a classification of recurrent classes, or is it just?
So classifying the orbit of JG is a classification of recurrent classes. It's actually how we do it, because the proof is done using minimal invariance subspace, which are recurrent classes, because we are in a compact space.
There is some other question? No, so we can find. Tristan?